Hello, I'll just quickly go through the task that has been given for this particular problem statement. Here, I have made a robot Pinocchio package where I've implemented all sort of the core functionality, and I have this particular Python file where I have a node where the sort of core functionality of the required problem statement is generated. So I'll quickly just walk through all the 4 points that are supposed to be finished and just explain you from the result regarding how all of this works. Before that, I'll just go over a basic architecture. This is a node which is subscribing to the robot description topic, and then I've also created a timer, and hence we have two callbacks: a listener callback and a timer callback. Now the reason I'm running the rest of the code in the timer callback is ideally we want the code to run the sort of calculation to run in a certain loop uh, at either in whatever algorithm that we're going to use later, and it is not good to have sort of the extracting data part within the same function. And so this has been done here, and it's also helpful in debugging since the function randomly generates configuration and then calculates it again and again, so it is easy to sort of debug any sort of um, functionality that has already been implemented, and we want to test in various configurations how it will exactly perform. So without further ado, I'll just move forward with this. So here I'm already running the simulation. I'll just close it and show it once more. For any sort of package for a robot, it's the usual sort of criteria is it's robot name underscore robot, and it has a robot name underscore description package which has a launch file which is going to launch a bunch of basic stuff. So the robot state publisher launch file here just launches the robot state publisher and couple of other things, whereas the show.launch here it includes the other launch file, and in addition it also launches RViz for visualization. So we're just going to launch this file. We're going to launch this launch file here so that we'll be able to see the simulation. So ROS to launch, name of package is Tiago, description, and show.launch.py. So yeah, it's generated all of this, and we can see that it's a robot with this particular end effect. Now that we have this, we know that the robot state publisher is also publishing the URDF on the robot description topic, and we will just run the code that we have written here. So right now, what we would expect is uh, the first task where it's just getting the text, getting the data from the robot description topic and converting it into a Pinocchio model. So let's just go with build and ROS to run, name of package robot Pinocchio, and name of the node file. So yeah, we can see here that it has successfully retrieved the model. It's found 30 geometric objects, and it is generating random configurations for the robot. So it identifies on its own the number of joints that are there in the robot and starts producing random configurations. Currently the configurations are being produced, so for each one DOF joint it is in the range of minus pi to pi, and that is how the random numbers are being generated. Moving forward to the next task, which is to get the transforms. Here again, whatever configuration is being calculated, we calculate the forward kinematics, we update the frames, we calculate joint Jacobians, and then we update the frames again. And because we did calculate the forward kinematics earlier, we just have to log the transforms, which are easily accessible from the data structure that is given in Pinocchio. So again, I'll just build it and run it again, and I'll stop the node here so that we'll have a moment to look at the solution. So again, firstly it's taken some configuration, and now it has printed the homogeneous matrix for each of the joints. So we can see that the name of the joint is written here, and the 4x4 homogeneous matrix. So wheel left joint, and then it's 4x4 matrix, and similarly for all the joints. And this is happening in a loop, so again it's taken some other random configuration and then printed again for the same. Moving on, we'll go forward to task 3. Here we have the frame Jacobians for the end effector. So we have identified an end effector frame ID, and that is what we'll be using. So again, I'll just compile and show the result. And let me just cut it here so that we can have a moment to look at this. So again, choose some random configurations, found out where the end effector frame is, so the rotation matrix of the end effector frame and the position of the end effector frame with respect to the world origin. And for two frames, that is the end effector frame and the arm tool frame, it has printed the frame Jacobian matrix as well. So that is what we can see here, and it is quite clearly visible that there are 6 rows here, which stands for the standard 6 rows for a Jacobian matrix, and the number of columns is equal to the number of joints that are there in the system. So Pinocchio follows a structure where each frame is sort of attached to one joint, and so calculating the joint Jacobian for that particular joint or the frame Jacobian for that particular frame in its world frame is the exact same thing, and that is what we see here as well. So moving on to task 4, where we have to calculate collisions. So firstly we add all collision pairs, then we compute if there has been any collision, and then we log whatever result we have gotten here. Again I'll just run it and show the result. Yeah, let me cut it here. Yeah, so we have a random configuration generated. Now it has identified 371 collision pairs. These could be pairs between the links of the robot itself or the robot or its environment and so on. So if you want to add obstacles in the environment, we can just add an object like before this line, and that will get included in the collision pair calculation. So it's found 22 pairs where the collision is occurring at this particular configuration. It's printed all the collision pairs where collision is occurring. Now it could be possible that some of these collision pairs are just the placement of the links in the URDF in such a way that they are always going to be in collision. So it is important that we identify those sort of pairs, and then so we can pass an argument here to add collision pairs, or before that basically where we want to remove certain set of collision pairs, and we can just remove those pairs. So eventually when we are going to have a collision checker, even if one of the pairs is in collision, we'll just assume that the robot is in collision. Here we are also printing what is the state of the first pair. So here it is not in collision, and again the same thing is being repeated for the other configurations as well. Moving forward to the final task, the payload calculation. So let me just sorry. So for the final task, okay, here sorry, build and run it. Yes. Okay, so there's been some issue, but anyway we have gotten the result that we were looking for. So again, for whatever random configuration, it has found the maximum payload capacity with the algorithm that has been mentioned in the proposal. So for this particular configuration, the maximum payload that it can take is 213. And the torque that is required for each of the joints for this particular payload has also been printed here. So you can see that for a given joint ID, the torque that it has to produce for that particular payload and the limit that that particular joint has. So it is visible that all the sort of effort requirements are less than the limit, and this one is the one which is close. So joint ID 5 is the one that will saturate near when it is in this configuration and the payload is being increased. So joint 5 is the one where the payload is the sort of torque is closest to its effort limit. Similarly, we can also have let's say if we give a payload and ask it to ignore the effort requirements, we'll just get the joint requirements that the joint is supposed to be produced. And in this way, for a given payload, we get the joint effort requirements as well that can be done here. And that functionality is not implemented completely, but that is also mentioned in the proposal as to how we'll do it further. So yeah, that has been here. All of these implementation has been done as part of different functions here, and it's pretty straightforward just what all has been done here. And just to add, the assumption that is being made here is that payload is essentially a downward facing force on that particular frame, on the end effector frame. So if I just go to this function and show you, so the maximum payload being calculated Let me just show you how it does that. So yeah, we can see that for a given payload, first we get a null force. So here the null force is essentially for each of the joints, it's 6 cross 1 vector of 0. So the 6 vector is for 3 for linear forces and 3 for moments. And so we generate a null vector, and then for the end effector frame that we have identified, and for the joint that is there just before the end effector frame, uh, we are adding the payload as a negative load on the z axis with no other moments and other directional linear forces. We can in fact in future make the algorithm more robust, where we can give payload in 6 dimensions, so that will just change whatever is there here and it will add forces here. And if we want to add forces on other joints as well, that is also quite possible by changing the frame the joint that is being input here, and then adding that payload as well, and the rest of the algorithm just calculates everything on its own. So yeah, that is it from my side. Thank you.